So today is the fifth day and I already worked. I'm gonna put the sped up evidence later in the video after this short explanation. What I did today was basically implement this paper with the help of the tutorial of Carpati, and yeah, it's basically this architecture, which is a multi-layer perceptron, these main two layers, and it's it uses a different architecture from the bigram, but it's like an extension of it. So in the bigram, what we did is uh, we use individual characters and we predict the next character based on the previous one. That's it. So here, instead of using a bigram, we are using a trigram. No, like 4 elements. Yeah, because we are using 3 characters in order to predict the 4th character. Although in this paper they use words instead of individual characters, but the idea remains the same. So the characters are treated as inputs, and instead of using one hot embedding, what we do is we actually use a vector embedding for each character. So we're gonna have a tensor of the size as many observations times 3, which are like these three entries. It's one per each character, and then times the vector embedding, and then we multiply by the weight. It's a multi-layer perceptron. It's just a linear combination. Apply tangent, and then we apply the second layer with more weights, but the output is the alphabet, because in this case we are treating characters. We only have 27 characters. We are not using a vocabulary of 10,000 words, and we apply softmax, and we get a vector of probabilities that we are going to use, and that's it. And this is the implementation. Just to go quickly, instead now, if we are given these 3 entries, the next character, for example, we're treating the same problem as we have names, and we want to predict a character of a name based on the 3 previous ones, okay? And we can get all these like observations based from a given name, and the most important here is the embeddings. Here at the beginning, just for testing purposes, we take each character. What we did, it has an embedding of just 2 elements, okay, of a vector of 2. Yeah, that's it. But we then increase this, so it's fine. And this is the first layer. We created 6 neurons, and in order to do this, it's basically we want to multiply the tensor, because this is the embedding, and this is this embedding. It's for each entry, and there are 3 entries, so it's 3 times 2, and this is for every element in the dataset. So if we have 32 in this case, just to prove, then the size is 32,3,2, and we want to multiply this by the matrix of weights. So what we do is concatenate this. We use this function view, and we concatenate these 2 elements. 3,2 is 6, and then PyTorch can infer the other dimension, and we then make the matrix multiplication, and then we pass this as an input of a second layer, and the other layer we just take care that the output is the vocab size, which is 27 in our case, and we apply the loss just to see. And in this case, yeah, basically this is the loss. We are computing the maximum likelihood. We are optimizing for it, and so it's the same as minimizing the loss. In this case, the loss is going to be the negative log expectation, the log mean, because basically for each entry, for each triple of entries, we're going to get a target character, and that target character is going to be, because of softmax, a probability vector. So we can take that specific probability that should be as high as possible, and we're going to do this for each entry in the dataset. And then if we compute the mean, we get the actual loss. And it's the same as using directly cross entropy. And that's it. So, but yeah, the thing is that it's better to use built-in functions in PyTorch, especially because there are numerical stability issues. For example, if the loss, if you apply, if you try to do this, like cross entropy to some value that is, I don't know, very positive, then you get problems with infinity. If you exponentiate, for example, if you exponentiate a very small number, a negative number, you can get a very small number and it's fine. But if it's very large, then you get infinity, and infinity is not a number, and then you get errors. So what PyTorch does under the hood is that it subtracts the maximum number in order to have numerical stability. But yeah, and then this is a generalization of what we did. It's just making it a bit pretty, and also implementing a little bit of mini batch. This is the output, and this is how the embeddings look like. It just in the first 2 dimensions. In the end, we did for here we did 10 embeddings. So every character is represented in a 10-dimensional vector, and we can see here that after the training, these are how in these 2 dimensions, this is how they behave, like how close the certain characters are to one another. But they could be close in here, but not specifically in another dimension. And yeah, these are the words that we get, the names that we get. And I mean, here in this example, I just wanted to try, so I said, give me the names that start with AL, and you predict the next ones. And are these ones. No, ALE. Yeah, start with LAE, and you predict the next ones. And that was it. It was really fun. Now I add the video, sped up. Alright, see you.
Okay.